Today, we're very happy to have our very own Neal Weiner of New York University telling us about S8 and the Hubble Constant and understanding them and steps. Thanks.
Thanks. So, first off, let me just say that I'm trying to target this talk at, astronomy graduate students, not particle physicists graduate students. So, a lot of you can just go, if you haven't gotten your lunch, if you don't eat lunch, you do have lunch, you can go get it, eat some of it, come back in 35 minutes, and then that will be the part.
Well, because astronomy graduate students haven't heard of H.
I'm going to talk about H in a particle physics context.
I saw.
And I'm going to talk about how you think about it in the early universe and all that. So, So we were saying that you also can leave and come back in 35 minutes, and you'll be fine.
I'm going to learn a lot.
I just mean, setting our expectations about that's this early in the semester, so I want to make sure I'm bringing you on. This is work that's based on 2 papers with this is also this one is in Berlin with Daniel Loney, Asher Berlin, Melissa Joseph, and Martin Schmaltz on this one. And the same people minus Asher, but plus C. Ryan, so he's a graduate student at BU. Melissa Joseph's a graduate student at BU. Daniel Loney is postdoc at BU. Martin Schmaltz is a faculty at BU who I've known for a long time, was collaborating with, and Asher was here and is now at Fermi. So,
and Martin's going to come in the spring.
And Martin's going to be here in the spring, and he's super nice and very friendly. Interesting to talk to, extremely tall.
So hard to talk to?
That's right. Yeah. So, okay. So, here's my outline. I'm going to start off by talking about what is S8, and I'm going to talk about what is H. Then I'm going to do an early universe primer for people who don't think about the early universe. And then I'll talk about step dark sectors, which we refer to as WZDR for a reason that I'll explain later. And then, there's Disney, there's Disney Plus, there's ESPN, there's ESPN Plus. We thought it's all the rage, so we wrote a paper with a plus. And I'm going to talk about that. Okay. So, first I'm just going to start with some very, very basic definitions. If you want to know more about especially S8 or sigma 8, you should talk to cosmologists. So, what is S8? Well, let's not start with S8, let's start with sigma 8. So let's imagine that you draw a box in the universe. Right? So you just go out and you draw a box, and the size of that box is approximately 8 megaparsecs, not exactly 8 megaparsecs, but about 8 megaparsecs. And then you just add up how much matter is in that box, and then you go around and you look at a whole bunch of different boxes of the universe that are of that basic size, and you ask, well, what's the variation in the amount of matter that I see in those different boxes? Then that quantity is sigma 8. So sigma 8 is the variance in matter in these boxes at size 8 megaparsecs. It's not exactly 8 megaparsecs because it's scaled by the Hubble constant, which we'll come back to. Well, we'll come back to Hubble constant. We'll come back to why this particular number.
Neal, can I ask a question?
Yes.
What's special about 8?
Well, you can ask the cosmologist, but it's sort of at the scale where it's at a scale where things are starting to become nonlinear, but are still linear. So you think that you've still got calculation control on things, but it's sort of order 1 size fluctuations. That's the only reason I can see. I don't know.
Yeah, it's because for galaxies, sigma 8 in spheres of radius 8 are the sigma 8 is about 1 for galaxies of Milky Way mass. Yeah.
And is the technical definition of sigma 8, I actually don't know. Is it a hard sphere or is it a Gaussian window?
I think it's a hard sphere. Right?
Yep. In configuration space.
Yeah, and it's actually right. Yeah. So it's It's not literally this, but this is your intuitive definition of what it is.
And I think it's also linearly extrapolated.
Yes, it is.
So it's
So it's actually really nice because it
it's
is
non-observable. It's great
It's
because
not.
it's non-observable.
It's right. The nice thing about this is it's something that you can directly calculate because you assume everything is linear to get it. And then the problem becomes somebody else's problem in terms of connecting that to actual data. So theorists are doing a great job of taking a theory, calculating this number, and then it's beholden to the observers to figure out how to connect that. Not our problem. People will talk about this number. Which is S8, which pulls out the amount of dark matter in the universe, the amount of matter in the universe. This turns out, and Mike can tell us why, this is a better observable to look for, it's an easier calculation observable. But this is the thing that we actually calculate and talk about, and this is what people will talk about the tension as line with it. But it's saying, to the extent that you think that you know omega matter, it's the same basic quantity. We're talking about whether or not things are fluctuating at this particular scale at the level that you think. And the current numbers, there's DES and KIDS, provide two different numbers that you can combine. And if you go to, there's a white paper on this that will tell you that the combination is 0.768 plus or minus 0.016, or you can go and you can use, you can fit what you think the amplitudes of matter are in the CMB, and extrapolate them forward in time, and you get a value of 0.834 plus or minus also 0.016. And this is around 2.9 sigma. So it's not like a huge life-altering tension, but it has the prospect of becoming a bigger tension. And for whatever reason, if you go to a lot of these talks, people will get up and tell you, oh, that this is something that they're really looking at. Yeah.
So with the tensions, has anyone tried to measure for a larger scale where the fluctuations are not close to 1, to where we can rule out?
I mean, yes, right? You guys measure it at scales that are much larger.
Yeah,
As well
I
as
mean,
in the CMB.
Yeah, I think these numbers are if you look at where the constraints come from, they're actually larger scales. At least, I actually don't know about the weak lensing, but for the redshift space distortion constraints, effectively the constraints are from larger scales.
But that question is a great question because there's a scale dependence to this tension, and I haven't seen a scale dependence to the tension.
Yeah, I was just wondering if,
That's a great.
yeah, like if at large scales, do you still have a tension that would correspond to some of these weird theories? That
So my understanding, and I don't know how to, and I can't quantify this for you, but certainly when you look at the people's approach to this, the assumption is that on much larger scales than this, lambda CDM works very, very well. You can extrapolate forward, but I don't know how much larger scales you can actually get to in terms of the similar kind of measurements, right?
Well, but is it true? But you're not saying that if I took S100, we would find agreement.
At some point, you would think you would find agreement.
Well, at this point, I would think I would find agreement.
Yeah.
So.
Yeah, I guess this is a good question. Certainly, the approaches everybody takes in trying to address this is trying to solve this. Because if you look at the CMB, where you have measurements of what you think the power spectrum are on those much larger scales, then I mean that's sort of how you normalize things, right?
But then again, some of these warm dark matter models, whatever, don't have to cut it.
Right. So
But Neal, to understand, so the tension, because what one does at CMB is not that one looks at the corresponding scale and compares it to, right? One that does the whole CMB data and extracts from there the power spectrum.
and then you extrapolate to the scale. Yeah, no, I'm just saying that the CMB probes much larger scales.
Is it a coincidence that these standard deviations are the same because it seems like the data that you take are much different?
There's an anthropic solution to that problem.
If it weren't the same, we wouldn't be able to ask that question.
See? I told you.
But as Anthony was alluding, right, it seems like if you believe that lambda CDM works well on large scales, but at this scale, you think that it's maybe not working so well, then you might say, well, I want something that looks sort of like lambda CDM on large scale, but looks something different on small scales. And so last week we had a talk where they introduced some fuzzy fraction of dark matter that changed its behavior on small scales, and people think about all sorts of things. But the critical thing is on large scales, you think lambda CDM works, and on small scales, you think lambda CDM doesn't work. So you want some sort of model that's going to make that transition. And S8 is like way outside of my wheelhouse, so I apologize for not being able to answer those questions. Let me move on to something also that is outside my wheelhouse, which is H. So as Mike so pointedly noted, astronomers do know H. So you have Hubble's law, right, that relates the recession velocity of a distant galaxy, well, not too distant galaxy, to its distance, right? So you measure how far away it is, you measure how fast it's moving, and there's this proportionality constant. And if you, certainly I think, I'm not an astronomer, but certainly I think that if you talk to astronomers and you say, what is Hubble, they'll say it's this, right? It's a relationship between how far away things are and how fast things are moving away from you. And the number is about 70 kilometers per second per megaparsec. And if you are in my physics 1 class, which I don't think anyone here is, then you would have had a problem on a recent problem set where you were asked to convert this into its units, make this into its most limited units. You would have found that this is a 1/time unit, which is 2.27 times 10 to the minus 18 inverse seconds, or about 14 billion years. And you look at that and you're like, well, that's coincidentally really, really close to the age of the universe. Is there a good reason why that's the age of the universe? The answer is yes. And one way you can think about this is that if you have a galaxy which is this far away from us, moving that fast away from us, you ask, well, how long would it have taken at that speed to get from right on top of us to where it is now? You find that this is how long it would have taken, or the inverse of this is how long it would have taken to get from sitting on top of us to where it is. Or another way of saying it is if you ran the clock backwards, you say, well, how long would it take to land on top of us? It takes h naught inverse time to land on top of us. So while you might say, h is this relationship, if you are thinking in other ways, you can say, well, h naught, I want to think about it as a time scale, and that time scale corresponds to roughly the age of the universe. And in any given cosmology, there's a prefactor that's going to tell you how old the universe is. That's h naught time inverse times some number, but that's a very calculable number. The scale which is set that tells you how old the universe is always h inverse, is how old is the universe.
I would comment there, Neal, that I think that's why the universe's age is known so precisely, fundamentally, is because fundamentally it's a kinematic argument with dynamical corrections.
I mean, if you want to say that you know the universe's age so precisely, then you'd have to say that you actually know h not very well, which, right now we're saying we don't. So I don't know.
Yes,
exactly
you have to argue that the age of the universe is not known very accurately.
You would, it's not. I mean, if you believe these solutions to the Hubble tension, it's not actually known that accurately. Because, I mean, fundamentally, right, if you take lambda CDM and you use the Shoes value and you use the Planck value, you're going to get two different ages of the universe. Significantly different, right?
No. But within, good, great.
But with, it'll be a 5 sigma difference, right?
Yeah.
So, and if it's how old the universe is, then it's also a measure of how far a signal can travel in that same amount of time. So if you say, well, how far can a light signal travel? A signal can travel the distance ch inverse, or if I have a sound wave, that sound wave can travel a distance which cs is the speed of sound for that wave, cs h inverse. And again, with prefactor is dictated by like how precisely your cosmology, but this is basically the scalings of how far any signal can travel in the age of the universe at a given time. Okay, so that's why I was saying that I wanted to take a moment to talk about what is h, because it's important not to think of it as just this relationship, but it's also a dimensionful scale that's setting how old the universe is and how far any given signal can travel in the universe at any given time.
Yeah, I came in late, so you might have already said this.
Yeah, I already did. Yeah.
But in like 140 billion years, H naught would be pretty much the same.
Yeah. I didn't talk about that, and that's yes. All this changes if there's a cosmological constant, which there is going forward, or if you're an inflating universe, then that also changes the sound horizon and all that. So, but I'm kind of in a sort of like perturbation of our current universe. This is definitely a good intuition. So don't go too far to the current universe, and it's back as far as I'm going to be talking about. These things are good statements.
Sort of an odd coincidence.
Yeah, it is. Okay, so let me now take a moment to do an early universe primer of how I want us to think about the early universe for people who don't think about the early universe. So you can take our box, the same box that we were thinking about before, or a different box, and we look at it in the universe, and as the universe expands, we think of that box as expanding. So the sides expand, all the distances between objects inside expand, so things that are close together become stretched out, become farther apart. And so we like to have some variable that we use to keep track of this expansion, and so we typically call this length scale A. So A you can think of as the side of some generic box that you pick and use to keep track of the universe as it expands. And so A is monotonically increasing as the universe expands. And we can then use that to talk about how different substances in the universe evolve. So for instance, if I think about one of the ways we like to categorize stuff in the early universe, or currently in the universe, right, is by keeping track of its energy density. So you can look at, say, the energy density of matter. The energy density of matter is the mass of whatever the particle is times the number density of that particle. And as the universe expands, the number density, so if I think about the number of objects in this box, the number of objects in that box stay the same, but the box gets, expands as volume. So the energy density of matter evolves as the energy density at some given time times whatever the size of the box was at that time divided by the size of the box at some later time to the third power. Because you're just saying that box got bigger by that length scale cubed. And you can ask the same question for, say, dark energy, right, as Matt just did. You can say, what about for the cosmological constant? Well, for the cosmological constant, it's just stuff in the space, and the box gets bigger. The amount of stuff per unit volume is the same, so the energy density is constant. And then you have the question about radiation, which is the other one that we care about. And radiation is interesting because you can go back to the same box and you can say, okay, I've got a big box of, let's say, non-interacting photons. And as the universe expands, that box expands and the number of photons stays the same. And so you say, well, should the energy density in photons also redshift in the same way? Should it also dilute like volume? And the number of photons does, but each individual photon you can think of as stretching out and its wavelength also increasing. So the energy density of radiation is what you started with times A naught over A cubed for the volume, and then times A naught over A for the fact that you're also stretching out the wavelength of the photon. So energy density in radiation dilutes faster than energy density in matter, and so we end up with this picture you see all over the place of the different components of the universe, where you have the logarithm of rho versus the logarithm of, pick your favorite time variable, could be A, and that if you go far enough, currently the dominant thing is cosmological constant, followed by matter, and then way less is radiation. If you go back in time, matter takes over, and if you go far enough back in time, then radiation takes over. So if you go way back in time, the universe is full of radiation, and that's the dominant form of energy density.
This is a ridiculous question. I don't disagree with anything here, but one weird thing is doesn't this description depend on choosing a rest frame? This is the 0, component of a stress energy tensor. So if you change coordinates, you would get something. Do you have to make this argument in the rest frame of the Big Bang, or is this statement coordinate free?
I would not think that it would be coordinate free. You have to choose some slicing, right? Some time slicing.
So that's effectively like choosing a rest frame.
Yeah.
And the rest frame you chose is the one in which the average velocity is 0.
Yes.
Sorry, I mean, this comes from saying that the divergence of the stress energy tensor is 0 when that's in all frames. Then you parameterize in comoving times that form, but for sure the conservation comes from Einstein equation, so you can sure say that.
Yeah,
there must be. I was gonna say that. My point is that there must
I mean,
be
at any given point, this should be true. But the fact that you can say this relationship, I have to choose some time that I'm using to do that, and then I have some time slice throughout the universe. And I could choose a time slice where it's not that, where I go back in time in other places, and then in some places radiation is dominant, in some places.
Well, I mean, my complaint is more like the 0, component of the stress tensor depends on your boost. So if you travel very quickly through this universe, you will rank the components differently in terms of their 0, component. Because you blast into matter differently than you blast into radiation.
I think that's fair.
Yeah, that's kind of my issue. But I mean, it's trivial. It's just I don't love that we have to switch to non-coordinate free objects to describe our universe.
Yeah, although I should say that this is for people who know this is this is an important or interesting subtlety. I'm just trying to do this for people who have not taken an early universe course before, right?
Can I make a comment about rho radiation? So this is the component which is thermodynamically connected to the Big Bang phase. But if you were to add up the light from all the stars, since we have stars, that is still radiation, and it would be above the CMB line.
But all that radiation would have been formed at a time which is after matter has totally become dominant. So the extent that there's other stuff coming in here doesn't really change the picture in terms of extracting these quantities or going back. And it's not going to influence our ability to measure the CMB. But it's an interesting point, certainly. Yeah. But since we are, I'm on page 2, and so the other thing that I just want to emphasize is that if you're thinking about how to go back in time in the early universe, we know that the CMB, that the light left over from the Big Bang has a thermal distribution. Its wavelength is stretching out as the universe goes along, so we can characterize the CMB as characterized by a temperature. And that temperature is decreasing as the universe expands, so that temperature is the temperature at some time times, okay, yes, I know people can say we're going to have entropy dumps and everything, it's all very, very important, but basically the temperature of the universe is expanding like 1 over A, so to the extent that you wanted to use A as a clock to tell you, or you want to use time as a clock to tell you when you were in the universe, you can just as easily use temperature as a clock, except for it's an inverse clock in that the future is dictated by lower temperatures. So you could use T inverse as a variable that monotonically is increasing with time and telling you about where you are in the history of the universe. So you could, if you want to say, I want to talk about a particular moment in the history of the universe, I can talk about it in terms of A, or I can talk about it in terms of T, or I can talk in terms of the time. But any of these things are good clocks. And then the last thing that I'm going to say, and gosh, given this audience, I'd better be clear with my asterisks, is the fact that the Hubble constant in the universe is, well, I'm just going to, proportionality is proportional to the energy density, the total energy density. With the asterisk that I'm assuming there's no curvature, so Matt doesn't jump on me. So why do we care about that is because if we know the energy density at any given time, that's the same as knowing the expansion rate. And if we know the expansion rate, that's the same thing as knowing the energy density. And since we think that we know the temperature of the radiation, to the extent that we go back in time and we know the temperature, and that the energy density in radiation is given by the temperature to the 4th power, we sort of have a, with some caveats, we have a sort of a connection here where we can go between knowing the temperature, which is to say the time of the universe, to the energy density, to what the Hubble constant is at any point in the history of the universe. So I can go on to this diagram, and at any given point, I can tell you what the Hubble parameter is. And so I can tell you how long the universe has been around then, how far signals have traveled, and all of those things. So then that brings us now to the ability to talk about the Hubble tension. So the Hubble tension is the statement that the CMB, so Planck, tells us that the Hubble value is 67.27 plus or minus 0.60, and I think that they do it like this. The Shoes collaboration measures it to be 73.04 plus or minus 1.04, and there's different ways of doing these numbers.
So I hate to interrupt you with the technicality,
Yeah.
but the CMB does not constrain.
Yeah, just wait.
All right. The CMB does not constrain.
Just wait. Okay. Obviously, I'm going to talk about that. It's the essence of my talk.
All
I'm
right.
going to say that the value extracted from the CMB, measurements of the CMB, is this, extracted.
Well,
inverted.
sure, but not just the CMB. You cannot do it from just analyzing the CMB.
So you're saying
Not
CMB plus,
Plus BAO.
well, but BAO, you can make BAO independently, right? You can take an independent BAO measurement. I don't need BAO to get this, right? This number is not.
No, that you can't constrain it without assuming, or at least not at that precision, nearly that precision, without assuming flatness.
Yes, you have to assume flatness. Yes, you have to assume flatness. That's
And so BAO tells you that the universe is flat.
okay.
Yeah. Otherwise, you can't constrain it.
So how does the CMB hope to say anything to Mike's satisfaction about the CMB?
It can say lots of useful things. It just can't give you that number.
So you look at the CMB,
It wasn't a waste of time, those observations.
and there are hot and cold spots out there. And you can ask the question, if I look at the hot and cold spots of the CMB, are the hot and cold spots, uniform? Do I have more variation on different scales? And so we quantify this with the power spectrum of the temperature correlations. And you plot this versus L, which you can think of as some sort of angular scale on the sky, or rather an inverse angular scale on the sky. So high L corresponding to small scales. And you see these peaks where there's more, the amplitude of the fluctuations is larger. And there's a fairly simple picture of where those fluctuations come from, which is through thinking about these sound waves. So you have some overdensity in the early universe, and as the universe evolves, stuff can fall into that overdensity. Eventually, if it has enough time, it will feel the pressure, it will push back, it will come back out, at which point gravity will then take over and turn it around, and it will pull it back in, and then it will push back out, and so on. And so you see these oscillations corresponding to that phenomenon, where this first peak is corresponding to things falling in for the first time. Okay? And then the subsequent ones are for turning around, falling in, turning around, and so on. And so you can sort of very, very, very heuristically ask, why should this kind of a thing tell you something about the Hubble parameter? And you can say, well, look, if I know the sound speed of the stuff out there in the universe, if I know the sound speed of the plasma, then this corresponds to some particular angle. So we have some observer, they look out, they see some scale on the sky where I see very large fluctuations. And I can say, well, what size is that? Well, the size of that is there's some physical size, which is the sound horizon, how far that wave could have traveled at the surface of last scattering. And then there's some distance. Okay, so this is the distance to the surface of last scattering. And the sound horizon is, loosely speaking, the speed of sound times the Hubble parameter at that epoch, right? Because the Hubble parameter at that epoch tells me how long the universe has been around, so it tells me how far a signal could have traveled. And there's a lot of physics that's going to go into precisely what this CS is, including like how many baryons there are and things like this. But this is sort of how far this scale should be. Then you can ask, well, how far away is it? Well, that's the angular diameter distance to this particular surface, which is set by, again, how long the universe has been around. So this d here is something like, with some additional numbers, just depending on what our cosmology is, which we've measured well. It ends up with these two numbers. So the angular size then is just this. So you say, well, if I believe I know everything about how the early universe was, I think I know how much matter there was. I know lambda CDM. I know how many, I've measured now approximately how many baryons there are. I know how many photons there are by extrapolating it back. So I know this, and I know my cosmology, so I know how fast the universe is expanding at that time. And so if I measure this angular scale and I believe I know all of these things and all the prefactors, then I can extract this Hubble parameter, the Hubble constant today. And so that is the sort of indirect way that you pull out the Hubble parameter from the CMB, is by measuring, and in reality you do a broader fit and it's included in many, many things, but sort of physically, if you want to think about why should this thing be sensitive to it, it's because you measure an angular scale and you think you know one side of it, you think you know from your theory what this side should be, so that allows you to know what this side should be, and that side is just telling you how old the universe is, which is determined by how fast it's expanding today.
And I think Mike's objection comes in the fact that the dimensionless constant in there does depend.
It does depend on
flatness or dynamics.
Yeah, and the whole evolution of the universe in between, which is not constrained.
Yeah, no. So to get this, obviously, to get this right, you have to actually have measured how the universe has been expanding from the part of the age of the universe when it's been expanding the most, which is especially late.
My issue here is that it's always said that the CMB does X, and it's just not a true statement.
Okay, I didn't
It's
even
not a
step on any
complete statement.
toes. CMB plus the very, very critical supplementary measurements.
Yeah, WMAP would say plus X'd,
Yes.
but that's an old joke.
No, I remember WMAP plus X. I'm old enough for that. Although it's worth noting at this point that BAO, at least in terms of this phrasing, is a very, very similar measurement. Because what you're measuring then is you think you know the physics of what that acoustic oscillation should have been, and you're measuring an angular size, and you're inferring what H naught is from that. But it's a very similar set of parameters that are going into it. So we've already talked about solving S8, what kind of things people do. They try to build models that on small scales look different from CDM and on large scales look like their CDM. So how do people want to solve the Hubble tension? The way people want to solve the Hubble tension is you just look at this formula, right? And it's pretty clear how you would solve the Hubble tension, knowing nothing else. So you say, well, if I know this, and I thought I knew that, and I extract that, and that appears to disagree with somebody else, well, I have so many things that I can modify here. One of the obvious things I can modify is say, well, maybe I didn't know this as well as I thought I did, right? So I thought I knew how old the universe was at the surface of last scattering, but maybe I was wrong. Maybe the universe was younger then. And if the universe was younger then, it was expanding faster then, which means that it would have a younger universe now, which is expanding faster now, okay? Because I'm measuring this ratio. So people say, all right, let's try and jack up this H. But we already said over here that H, or I said over here somewhere, that H is directly connected to knowing the energy density. And so you say, well, I just need to add some additional stuff. That's the idea. And that's what a huge class of models that have attempted to solve this all involve saying, let's add stuff to what the energy density was at the surface of during recombination, so as to change this number, so as to change that number. So you go into your energy budget, and you say, what was this back then? Well, you have what we see now. And you say, well, we have the cosmological constant, but the cosmological constant we've measured very well at recent times, and it certainly does not look like it was doing anything interesting back then. So probably there's not our current cosmological constant. Okay, so I'm going to just X that out for the moment. Dark matter, really better act like dark matter because it's responsible for all the structure formation that we see, and we can make measurements of how much dark matter there is today and extrapolate it back. It's all part of this global fit, so that's tough to do. Radiation, similarly, we actually measure the CMB. We know how many photons there are in it. You can extrapolate that back, so that's going to be hard. But you've got neutrinos. Neutrinos, we think we know how many there are. We have a model, the standard model, so you can calculate how many neutrinos you think there should be. And it could be, just broadly speaking, that maybe there's just other stuff, right? Way back in the history of the universe, there was other stuff that was populated, that contributed, that was radiation that doesn't interact with matter. So people talk about it as just dark radiation. And that dark radiation would kind of come into this rho nu. It would kind of act like rho nu, but it would increase the Hubble rate. And so people, as soon as there started being some indication of Hubble tension many years ago, this was suggested right away as a solution. People said, well, if the Hubble parameter we measure from the CMB and all the other very important critical cosmological measurements that were associated with it that allowed us to extract the cosmology that allowed us to get the three-factor
It's not a textbook.
disagrees with the direct measurement of the supernova, which is not a direct measurement because it also relies on the calibration of the Cephids to build your distance ladder and things like that. But if they disagree, that the one way to do that would be to have this radiation. But the problem is people quickly found is, and if you ever do a CMB fit, and if you don't have to, I would not encourage you to, is that there's always a question about what you're holding constant when you do these things. There are many, 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 many parameters. And when you say, if you say add radiation, then that's going to do something. You always have to say, if you add radiation and are holding the following things fixed, are you holding matter radiation equality era fixed? Are you holding the current amount of matter fixed? Are you holding the current Hubble parameter fixed? What are you holding fixed when you do that? So with that caveat, if you try to keep the late universe fixed and you add additional radiation, what that tends to do is to damp out these higher modes, and that is not in good agreement with the data because the energy density in those overdensities, as they add more radiation, can stream out and flatten these things out, and that's not seen. So it became quickly pretty clear that just adding some additional, people refer to as free streaming radiation, was not a good fit to the data. So people proposed instead adding what people refer to as strongly interacting dark radiation, or SIDR, which is instead of neutrinos in our current universe just fly entirely past each other. And they don't talk to each other at all. And so that allows them to smooth out inhomogeneities pretty efficiently. But you could imagine adding dark radiation that had interactions with itself, and that was harder for those particles to stream out over densities.
But is not radiation constrained by BBN?
Let's come back to that. I mean, yes, it's constrained. It's constrained weakly by BBN. Not as the stronger constraint is certainly from.
So within BBN, you can solve your problem.
Let's talk about that because it's an important question and it's an important question. So people suggested this. This is not us. Many people suggested this, and it can do well with the TT power spectrum. But now we have more data on polarization, and if you look at the data on polarization, you see that that model is in disagreement with those. Not terrible disagreement, but it certainly doesn't take you from a 5 sigma tension down to a 2 sigma tension. It takes it from a 5 sigma down to a 3.5 sigma tension, or whatever it's worth. So that's where we come in, and we proposed an idea. That idea we refer to as WZDR, which stood for West Zunino dark radiation, and it turns out because this gets packaged into a particular model of particle physics that was known as the West Zunino model, but that's not important. What's important is what's actually in the model. So let me tell you what's in the model. There's a fermion psi, which if we take be massless, and there's a scalar phi, which has a mass around an ED. This is pretty much if I take away this mass of an EV, this is really pretty much exactly this model, okay? That's all I'm saying, is that it's just some particle psi and some phi that allows them to scatter off of each other, and it's some fluid of all these things bouncing off of each other. So you have processes, right, like this, where this is the phi and this is the psi, and you have processes like this, where they can convert back and forth, and they time can go both ways. So this is just a fluid of two particles that can go back and forth and be tightly coupled to each other. So this is, in some sense, just a realization of this. So the only thing that we did was we said, well, you know, if you have this particle here, you should at least think about what would happen if it had a mass. And what if it had a mass that was relevant at the temperature scales that are under consideration? You might say
these particles are singlets under the standard model?
Singlets under the standard model. So right now we're talking about something which is entirely decoupled from the standard model, and with a mass of around an electron volt, which is just a little bit higher than the temperature of the CMB of matter radiation equality. Why would you think an EV? Well, there are a couple of reasons why I would say we should think about this mass scale. One is, it turns out that the CMB and the data we're getting from the CMB now and the data we're going to get from the CMB in the near future is sort of sensitive directly to temperatures when the universe was at temperatures which were comparable to, you know, EV up to tens of EV. So if there were a mass of that scale, this is sort of the data set that would be interested. So if you want to think about a model like this, this is the time to think about that model, because in 10 years you'll know that it's dead. And 10 years ago, you could have talked about it, but you would have had no hope of testing it. So now is sort of the time where you can talk about these models and have a hope to say something about them in the near term. The second thing is that we already know from various things that the EV scale is kind of an interesting scale. Neutrinos have mass, which is sort of about this scale. You say, oh, but doesn't that come from the seesaw mechanism? Well, who knows what it comes from? You know, maybe there's something which is setting an interesting mass scale for the neutrinos, and it happens to set it for this as well. The cosmological constant is not too far off from this, and if I convert it to take the 1/4 power of it. And finally, if you are playing sort of like beyond the standard model games, you get all sorts of, you know, ratios of various mass scales, and this mass scale is very close to something like 10 TeV squared over m Planck. So if you believe what you would say if you're a particle physicist, you'd say, well, if there's a mass scale which is 10 TeV in my theory, and I have higher dimension operators which are mediated by gravity, then this scale would have come out. Right? So that's what you would say. So, you know, whether that's actually connected to reality is, you know, who knows? I'm just saying that there are plenty of reasons to say that this is an interesting mass scale. Probably the best of them is that it's going to be connected to, it is currently connected to, and will be connected to data that we're going to see very, very soon. So,
by the way, that's all connected to the point that the CMB spectrum is the spectrum of an A star. If you're an astronomer, an A star, which is like 10,000 degrees-ish, and the sun is what, 6,000 degrees, and the sun peaks at around an EV, which is good for chemistry on Earth. It's also, anyway, just comment, just astronomical context.
Great. So,
is this in thermal equilibrium when you say they're interacting?
They're in thermal equilibrium with each other, but not with us.
Yeah,
because it's.
But you're assuming they have the same, roughly the same temperature.
Yeah, I'm assuming they have roughly the same temperature. And that all connects back to, you know, early universe stuff that dictates what happened there. So, right. So why is this at all interesting? Why is this just not the same thing as that? Well, it turns out, I mean, there are different ways that you can do to calculate this. The sort of standard way that you would do this is you would say, well, entropy is conserved, and I go through a threshold. So I start with some high temperature where I've got both particles, and then I go through this mass threshold. And then below that mass threshold, I only have these particles, right? So all of the energy which is in the 5 particles needs to go into the psi particles, but more importantly, all the entropy that is in these 5 particles needs to go into the psi particles. So if I make a plot of this log rho, where this log rho is now the total of this sector versus inverse temperature of photons, okay? So I'm using the standard model photons to keep track of this. You find that it's decreasing just like a to the -4, like it would have, like any old fluid, until you get to a temperature where the dark sector is around the mass of this scalar field. When that happens, it goes like this, and then it continues to fall like k to the minus 4, k to the minus 4. So you can plot that as a ratio and say what happens here. What happens here is it's kind of coming along. The ratio of this dark sector and its energy density divided by photons is some number, right? Whatever it is that you start with. And then you get to some mass threshold, which is the temperature where where the phi becomes non-relativistic, and you get this kick up. And this kick up here in this relative energy density you can think of as coming from entropy conservation, or if you want, you can think of it as that you go through this period of time where this phi particle is not exactly radiation, so it's redshifting a little bit more slowly, diluting because it's got some mass energy that it needs to dump into the size. However you want to think about it, the upshot of it is ultimately you get this bump up here, and this bump up is just dictated by the ratio of the degrees of freedom that you have to the 1/3 power. So you can count up the number of degrees of freedom, so spins, flavor, whatever states that you have in your initial state. You can take however many degrees of freedom you have in your final state, you take the 1/3 power of that ratio, and that tells you how much this increases going through that step. And importantly, the energy density never increases, right? The energy density is always diluting, it's always decreasing. It's only increasing relative to what it would have been if it had been a simply expanding fluid. So,
Can I ask just
Yeah.
about, you called it Weissumino, but I assume the supersymmetry plays no role.
the supersymmetry plays no role except for that, I mean, it played a role, it plays no role. It played a role only in the sense that we were thinking about if you wanted to build a model like this, and you wanted this.
The question is, why did you need spin a half and spin 0? I mean, what's
We were
wrong?
trying to stabilize this. Ask if you have a scale, if you had these pairs of particles, then how would you make sure that that was stabilized? You'd say, well, supersymmetry, if the dark sector were supersymmetric, then you could imagine stabilizing that. And then, well, that's the Weissumino model, just a single chiral superfield with this x cubed interaction. So it has all the ingredients in it. It has some ingredients that we don't need. And like many papers, there's the path you take to get to an idea, and then there's the path that you would have taken there if you had started afresh with everything you know. And probably at this point we would not, I don't know if we would call that or emphasize that, because it's really just this. But at the time, that's how we were thinking about it.
So spin a half alone or spin 0 alone would not do the job.
Well, you would need two particles.
Okay.
You need two
Two
particles.
spin a half, 2 spin 0.
2 spin a half probably wouldn't work because you wouldn't be able to write down the direction. 2 spin 0 would probably work. A spin 1/2 and a spin 1 would work, but then you need a mass threshold. So maybe then you say, oh, I need a spin 0 anyway. Anyway, you can go through it. But really, what you need is this: you need two particles that are interacting and a mass threshold. That's what you need. So what does this do? So if you go back to your matter power spectrum, what is the sort of like experimental, what is the observational signature of this? Well, again, it's always a question about what are you holding fixed when you say, what does this do? And so when I say, what does this do? I'm saying, let's imagine you hold all the late time parameters fixed. So you can measure omega matter here today, you can measure the Hubble parameter today, you can measure all this stuff today, and I'm going to keep those quantities fixed and only modify things in the early universe. So let's imagine, for simplicity, that this scale here, remember this scale corresponds to some physical distance at some time. It's the sound horizon at some time. And that is the sound horizon at some temperature. Okay, so let's imagine that at later universe, when all these things were, when these motes came inside the horizon of the universe were being affected, you just have same lambda CDM plus this additional radiation. And back here, you have this, you have the same thing, but not equal to the latent kind of thing. Okay, so these are the two models, and there's some line here, and in the early modes, they're sensitive. They came inside the horizon and started oscillating and doing stuff when I had both particles, and these ones came inside the horizon when only the fermions were around. What's the effect? The effect is to basically take these peaks and shift them over. That's what it does. You can calculate that, and that's and so you can calculate to find out that's the right answer, and then you can go back and you can wave your hands and come up with an explanation as to why that's the case, and I can give that to you. Basically, that if you go to this particular angular scale and you thought that was when you had a couple of oscillations, well, actually, because the earlier universe was expanding at a slower rate, there was actually a little bit more time than you thought. So that particular angular scale has actually gone through a little bit more oscillation than you thought, so it's already on this downside. So the peak is going to be shifted to the left. I did not come up with that explanation until we had actually, run the computations and calculated and things like that. So if it had been the other way, I don't know if I would have been able to come up with an equally good argument. But so you do this, and you do this bit, and you find that H naught is in this range, 90%, with the best fit of 69.1. So it's certainly not taking you all the way up to 73. It's not even taking your upper parameter up to 73. So this is not going to take you to the complete solution of anything. But it improves your chi-squared by about 15. And there are different statistical tests you can do, and people argue for different statistical tests, and they all kind of end up with, roughly the same thing.
What's the number of degrees of freedom?
You're adding 2 degrees of freedom.
No, the total number of degrees of freedom.
Oh.
That's what matters for chi-squared.
Well, this is delta chi-squared, so you want to compare, this is delta chi-squared versus the CMB. So I have the same number of degrees of freedom in the CMB, and then I add 2 more degrees of freedom, and I can ask, how does the overall chi-squared improve when I add 2 more degrees of freedom? And I get this.
Oh, this is a likelihood ratio test, so I can just take the, okay. Fine.
Yes, and so then you can do things where you're assuming that
I don't need to know the number of degrees of freedom, you're right.
And then, but then you can make this different assumptions about whether that likelihood is Gaussian or not Gaussian or various things. But it all kind of ends up being something like a 2-ish and change sigma tension as opposed to a 5-ish tension. So I haven't even gotten to the plus yet. So let me tell you why I kind of think the plus is sort of an interesting thing in the very, very few minutes that we have left. You can go back to our posteriors, and you can ask this question: what is the redshift where you go through this transition? What is the redshift where this particle becomes massive? And the answer is around 20,000, okay? But it's not exact. So let me say what I'm drawing here. So if you did not include the shoes data, you only include the sort of non-late universe measurements of the Hubble parameter, then you could do the fit and find out what what the value for the ZT is, where this transition should happen. And the data have a mild preference for a transition, very mild preference for a transition, at a redshift of about 20 to 30,000.
And when you say the data, you mean the relative positions and heights of these CMB peaks?
Yes. If you add in the shoes data also, then it looks like this. Okay, so it becomes an actual preference, which should not surprise you because you've now said that it went from a 5 sigma to a 2.5 sigma. So that is going to be some preference, and it wants some sort. But it turns out that the CMB on its own and the CMB with shoes seem to want the same basic transition. And then you can ask, well, that transition corresponds to some temperature, and that temperature corresponds to some age of the universe, and that age of the universe then corresponds to some distance scale that we can observe in the universe today. And what distance scale is that? And if you then work this works out to a sound horizon, which is around 10 megaparsecs. So it's telling you, in this kind of a model, in something like this, it's telling you that something interesting is happening. Or if I map it onto cosmological scales that I see today, I would expect one sort of cosmology to be interacting and happening at scales that are smaller than 10 microparsecs, and a different cosmology, more sort of conventional cosmology, happening at large distances. So what kind of a thing could that be? Well, this is where the plus comes in. And the plus is, just imagine that you've got dark matter as well. So take the pi and the psi, add to it chi, still have lots of Greek letters left. And I'm going to add some interactions where that chi can now also scatter off the fluid. Okay. So what's going to happen as I sort of go through my universe? Well, at high temperatures, dark matter has got some additional viscous drag on it that's going to slow growth of structure. But then once I go through this mass threshold, this interaction basically turns off. Okay? Once when the early universe is, when we're at temperature is much higher than the mass of this particle, this interaction is sort of stays marginally relevant. Once you go through this mass threshold, this interaction turns off almost immediately. And so you go through a period where you say, in the early universe, dark matter has some additional viscous drag. In the late universe, it's just lambda CDM. And what's interesting is that if you do the fits, the data would prefer there to be some sort of a transition at basically the same redshift. So you can do the fit with the CMB plus the data that are telling you sigma 8, but not include the supernova data, or you can include the supernova data and not the S8 data, or you can include all three, and they all will consistently point to a transition at about the same temperature. And I don't know, obviously, that this is actually, the solution to anything. But what is kind of interesting, and the thing that I kind of take away from this is not like literally this is the model of the universe, right? But what I do kind of take away from it that's kind of interesting is that maybe what this is telling us is that there's something funny going on in the CMB at a redshift, which is around this. Something funny is happening. And that same redshift corresponds to a horizon size, which is roughly where we expect something interesting to happen for large-scale structure. So maybe this model is somewhere in spinning distance of something interesting. Maybe it's not, but I think it's interesting that these two scales end up lining up. I kind of pointed to the same thing. So I will stop there.
But didn't you say in the beginning of the talk that this 8 megaparsec is just some fiducial thing? It's not physically significant. And now you are telling us it is.
Well, I'm saying that that's where you see a deviation from the extrapolation. So
But didn't you guys have a discussion that you in fact see it everywhere? And 8 is just
8 is where you clearly see it. This is actually a discussion that we have to have, because certainly the way people operate and the way I operate it is that if you look at the data, and it's true that what you need to do is you need to actually calculate in your model this quantity, this S8 quantity, and see whether or not it agrees, which is, you're taking an integral of all these modes inside. So it's actually got, you're sampling modes that are larger and smaller than that as well. But the sort of intuition is that when you look at large scale stuff, it looks very much like lambda CDM. But it's true, I don't know exactly where that transition happens.
And also you promised to comment on BBM.
I did, and I didn't. I will now.
Okay.
So the amount of additional radiation that you need here, if I just took this, is more than I would want for BBN. Not a lot more, but definitely more than I would want. And if I put BBN into the fit, then it would hurt my fit.
So why did you conceal it?
Why did I? Because we already had enough things to talk about in this. In the paper, we don't conceal it. We're very upfront about this. But the point is that you see this kind of bump up that you see, right? When you go through these mass thresholds, that the effective number of degrees of freedom increases. And so if you're in a model where you see these increases in the number of effective degrees of freedom, it's not insane to think that after BBN, there was some transition like that that you're not talking about here, that took you from whatever you were there to some larger number. So our point is simply that really these are different N effectives, and obviously they're different N effectives in terms of you're measuring the universe at different eras, but they're also theoretically different N effectives in the sense that it's very easy to imagine scenarios where the additional degrees of freedom during BBM would be low, and then the additional degrees of BBM at later times would be high. And we see the increase directly in our model. We go through this mass threshold. And so you can imagine going through some other threshold like that earlier that increases the number as well. And so we decided that in our fit, we would just keep them separate because they are actual separate pieces of information.
So this question of scales seems really important,
It does.
and I just want to ask, Roman, can you hear us? Maybe Roman called off. Anyway, Roman.
Roman is the person to ask about this.
What?
Roman is the person to talk to about this.
Yeah. Yes, I can.
So
you hear me?
when people say S8 or F sigma 8 today, what are the scales that actually that constrains? Like what are those numbers that people report? What scales are they actually sensitive to? Because like in redshift space distortions, it's not 8 megaparsecs for sure. It's some larger scale. But do you know?
Yeah, it's scales which are smaller than 8, basically, or yeah, they wash out and they don't contribute. So it's actually, it's mostly scales are around, 7 to 50 or something like that. That contributes to sigma 8.
And that's true for S8, like the lensing based ones?
Yeah, I mean, the way, yeah, I would say, I mean, it's kind of, for lensing, it's a bit more tricky, I think.
Yeah.
Because you're projecting, so I think I would say it's more smaller scales, but.
Okay, thanks.
Yeah.
In the early days of trying to understand the Hubble or the cosmological parameters, we were measuring parameterized models. We had like omega matter and omega lambda and so on. And then people switched to a mode in which they tried to measure H of Z. So we just measure the expansion history kind of directly and not try to work in a parameterized model. You made an argument kind of indirect. You now took a very specific model and estimated a parameter for that model. But when you talked about its implications here, you kind of implied that you could see the expansion history inside the CMB. And if you can, why don't we create a new observable, which is what was the expansion history prior to the CMB?
Interesting. My only answer to that is that like I said, that explanation I gave you was one that I came up with, which makes sense to me to understand this heuristically. But that's obviously not how you don't get it like that. You don't get it. You start with your power spectrum, you propagate it forward, you evolve the energy density universe, you go through the step, and then you fix that at some late time to some other observables, and then see what the effect is as you vary.
Right, and it sounds to me like that argument is very dependent on the power spectrum. If I tilt the power, there's going to be some degeneracy.
Yeah, there are
putting features in the power spectrum and putting features.
There are definitely degeneracies. This is all under the assumption that I'm holding my late universe observables fixed.
Yeah, but anyway, there is potentially a way to recast this as a like just abstract it away from the model.
Are there any more questions that aren't me or David?
So, for what I understood, we need the mass of the phi to be around dB. A coupling with chi-chi, I mean, I know what the mass of the chi-star or the cutoff, can it be risky to correct the mass of the scalar if we need it very precisely on the EV?
Yeah, I mean, it depends on whether you want to go down the sort of like particle physics naturalist direction, and we can go down that direction. Or we can just say this is a phenomenological model. Right here is a phenomenological model, but to the extent that, whatever, if you want, you and I, we can say mumble words like supersymmetry and yada yada, and then we'll be fine with it. So it would not be hard for you to take what I wrote down here and make that not a problem.
Also, Neal, you said that this model will be dead in like 5 years.
Yeah.
What exactly should happen to kill it?
So the biggest thing that should kill it will be ACT.
So again?
ACT. They're going to have a very big data set that's supposed to come out in the next
What is ACT, sorry?
Atacama Cosmology Telescope.
Which is some radio thing or?
It's looking at the polarization at smaller scales. So it's ACT, and then Simons is like the next stage, and then CNDS stage 4. But I think ACT alone, the measurement of the power spectrum at small scales and the polarization, accurate measurement of the polarization at small scales, breaks enough degeneracies of these models that it would be really, really bad. And lots of models. I mean, that's one of the things that's exciting. It's not like my model is like the only thing that's going to get killed. There are lots of models that are going to get killed. And importantly, if there's some, if one of those models could be lambda CDM, right? So
Let's hope.
yeah, let's hope. I mean, I think that's what I'm saying is I think is exciting, is that you've been living in this era where you kind of skate by and maybe you just like have this, you know, tension pop out in H0, or maybe you have this tension pop out in S8, but you know, it's going to be very, very over constrained, and you're going to start probing these very small scales that are going to, impact a lot of models like this one.
It'll be a very worthwhile experiment.
Very
Thanks. Let's thank Neal again. So I think there are cookies over there, but if you want to continue bugging Neal. But it's not a technical form. No, it's not. You just say CP plus LSS, and then it'll be everybody. But it causes confusion. People really think it's just CP, and it's not. That's very annoying, especially when it's
that I can imagine being more enough.
I mean, just to.
Let me sound like
Very, very nice DOE.